All right, so that was quiz 3. That was the last like high stakes, stressful assessment until the day of the final exam. By the way, I've got some info about the final exam. The day of our final exam is Thursday the 9th from 10:15 till 12:15. So you've got 120 minutes for the test. There isn't going to be a water gems question on the test, but you should bring Microsoft Excel. I'm going to provide the same equation sheet that I've given you for both of the previous midterm exams, and you can also, once again, prepare a sheet of notes. And the exam will be comprehensive, going all the way back to the first part of the course, but proportionally more of the points will be earned on material since the second midterm. So you can expect a little added emphasis on the stuff that comes after exam 2. So like water surface profiles and the methods that we're going to begin learning today, channel design, sewer design, that sort of thing. There will be more points. But I'll probably throw in a couple of pipe flow questions just to see what you retained. So that's our final exam. More immediately, you've got the design project on the near horizon. Tuesday is when the final report is due there. And of course, the final report should include corrected and revised versions of everything you've done so far, as well as polishing up kind of your explanation and your overview of the method in such a way that think of it as you're writing a how-to manual to yourself 5 years from now. And I mean, that's not just strictly hypothetical. You may find yourself in a position where thinking, oh, I'm going to be a geotechnical engineer, or I'm going to work in structures, where suddenly you have to work on a hydraulics project because that's the only work around the office. And you may be glad to have kind of a reference manual on how to use water gems or how to do a pipe network design. But, you know, more realistically, it's just good practice to work on technical communications. And so that report is due on Tuesday the 23rd. It also has to have the financial calculations. Then on Thursday the 25th will be a homework assignment that covers some of the stuff that we're going to be talking about today, how to actually find the depth when you've got gradually varying flow. And I think after this homework 15, there's actually maybe also 2 other assignments, but I didn't want to list everything all at once because then you'd feel too depressed. I was really just, there's not enough room. So, any questions about the announcements? Have a pretty clear idea of what's happening and when? We're getting towards the end. This is class 26. I think we only get to 30, right? Is there just 2 weeks of classes? Right? Yeah, I think so. I think there's only 2 weeks of classes left. Yeah. All right, so we're almost through. Boy, that'll be depressing when it's summer and we don't have to sit in class anymore. Yeah, just sit waiting for the fall. All right. There are physical gauging stations that can tell you the exact measured depth of a river at a certain location. In West Virginia, there are only about 100 of these. These physical sites where there's a sensor that's communicating either to satellite, or more realistically these days, it's communicating with a mobile network and gives a real-time updates on what's the depth in certain critical streams throughout the state. And let's take a look at one of those gauging stations, and I'll take you to the USGS, the Geological Survey website, that illustrates, let's see, is this going to pull it up? It gives us the depth over the last week period. Here it's the Ohio River at Huntington, West Virginia. And the river depth here is regulated by a series of locks and dams on the Ohio River. And so it would be very unusual in an unregulated stream for us to have periods where there's just a totally flat horizontal line like this. But it's possible in Huntington at the Ohio River that actually the water depth could stay the same. Oh, this is precipitation. What am I talking about? Here's the depth. It is still a regulated stream, and you will see times where the pool doesn't seem to be changing very much. But if we look at the relationship between when it's rained, so here would be precipitation total over the past week. So it rained on the 14th. All right, right, so then if we go back here and look at the depth on the 14th was 26, and then the depth increased. So as you maybe would guess, there's a relationship between when it rains and when the river depth increases. But if you think about how important water is in the state of West Virginia and the number of stream crossings where there's a road going across a creek with a culvert underneath or a bridge, there are literally tens of thousands of spots in the state where there's a bridge or a culvert, but yet there's only 100 stations where they're directly gauging the stream depth. And so I mention that because it kind of illustrates the need for some sort of a method to extrapolate from a measured depth to what the depth is going to be upstream or downstream of the spot where you're actually measuring the depth. So for instance, if we're measuring the Ohio River at Huntington, then what does that say about the river depth at Green Bottom? We don't have a gauge at Green Bottom, but you can estimate the depth upstream by using a couple of methods that are incorporated into HECRAS, which is a program that was developed by the Army Corps of Engineers. What we're going to learn today and on Tuesday is the method that's working behind the scenes in these hydraulic calculators. So you're going to learn how to do the calculations manually by hand on the spreadsheet, because you should never really start using and trust a design program until you have a pretty firm grasp on what math it's doing and like what are the limitations when it doesn't apply, or what are the assumptions that it's making. All right, so the direct step method in some text is also known as the step-by-step method. Answers the question, if you have two depths, how far apart are they? So it's in cases of non-uniform flow. And remember, there's a variety of features that can cause non-uniform flow. If we have that's water that's approaching a drop-off, then there's a curved surface of the water. And in the recorded lecture that you watched for Tuesday of this week, you learned how to find the slope at just a single point, the slope of the water surface. But what is a little bit tricky is you can't use that water surface slope to find out the depth upstream and downstream directly, because the slope is changing. So we can say the rate of change at a single location, but the problem is that if you move upstream, then you're going to have a different slope. And so we have to have some method that accounts for not only the changing depth, but the changing slope as well. And what this direct step method does is it's used in non-uniform flow where you have steady conditions. So you are assuming the flow rate is constant over time, but non-uniform means that it's changing with respect to position because of a hydraulic feature like a change in slope, or a spillway, or a gate, or flow over an edge. And the calculations that we'll do are going to be looking at the midpoint between two sections. So we'll divide a curve up into pieces, and then we're going to basically numerically integrate based on what's happening at the midpoint between two pieces. The direct step method, here's a summary of the method. Now this water surface cross-section is showing us y1 is the upstream depth, y2 is the downstream depth, and because you have non-uniform flow, what that means is that the slope of the energy grade line, here it's labeled TEL for total energy line, the slope of the energy grade line isn't necessarily the same as the water surface slope, and that's not necessarily the same as the channel slope. So those three aren't parallel like they would be in uniform flow when we use Manning's equation. Here is what we are adding up. We're adding up all of the components of energy. So on the left side, what you can see, S naught times dl is how far above some datum the channel is. And so that's the slope of the riverbed bottom, S naught, times dl, the distance between the downstream and the upstream section. Okay, so these two sections are a certain distance apart. The channel is sloped, and so the Z2 is going to be higher than the Z1. So that's the first element of height at 1, and then there's the depth, Y1, and then we've got the velocity head. So Those are the three terms that account for energy at location 1. And then as the water is flowing downstream, look at the slight subtle differences that we have on the right side. Here at location 2, we're saying let's measure the elevation relative to that location. And so the datum is at the bottom of the channel. So now we don't have any term that's related to the slope of it or how far upstream. We're just saying we're going to measure the energy and the depth starting at location 2. So then the terms are the water flow depth, the velocity head, and then the energy loss. So S sub F, remember the slope of the energy grade line is related to the resistance that the water encounters as it's flowing downstream. And if we have uniform flow, so if Manning's equation applies, then S naught times dl would be equal to S sub F dl. So uniform flow, if they were parallel, then that means that the delta Z is the same as the H sub F. But that's not the case here because we don't have uniform flows because the depths are different, Y1 and Y2. So this energy loss isn't the same thing as the delta Z. So just making that point here, in non-uniform flow, the energy loss and the delta Z are not equal. So we can rearrange this expression to find the difference in energy between 1 and 2. So if we want to find out what is that energy loss between the 2 points, well, we just find the difference in the components of energy. So it's the depth and the velocity head, the difference at each of those 2 locations, the difference in depth and difference in velocity head. And so another way of doing that is it's the difference in slopes times dl. Now, what we're going to be doing is taking a look at the characteristics of what's happening in the middle between the 2 points. Because remember, the whole issue here, we're trying to predict how much deeper or shallower the depth is upstream. So we'll have some point where the depth is known at one spot, and then we're going to try and find out what is the depth somewhere else. So we're starting with a location where we know the depth, and we're trying to see how much deeper or shallower it is somewhere else. And so what we're going to do is divide it up into pieces, lots of little pieces, and we're going to ask ourselves, well, how curved is the water shape between those 2 points? And we're going to analyze the curvature of the water shape, and that will tell us how far apart they are, the distance in that segment. So the dl, the distance between the 2 points, is related to how much energy loss there is relative to the difference in slopes between the channel slope and then the average of the slope of the water, the energy grade line. So this bar here, S bar, just means consider the energy grade line at the upstream and the downstream location and average them together. This method seems pretty abstract until you actually have to apply it, and I think one of the best ways for me to systematize a process and a series of equations like this is to come up with a spreadsheet example that illustrates it. So that's what we're going to do today, and if you have your computer with you, you're welcome to start up Excel and follow along. If you don't, that's fine. Of course, this is going to be recorded, and you can kind of just watch and absorb and then work through the example later. Either one will be fine. So while your computer's booting up, let's take a look at what's happening here. Why is there gradually varying flow? We have water flowing downstream, and originally it was flowing at the normal depth. So way upstream here, we could have found the depth upstream because we know the N value, we know the width of the channel, we know the channel slope, the flow rate. So all of the things that we need to use Manning's equation are provided. And so we could find, if we go far, far away from this disturbance, we could find what's the uniform flow depth. But as the water gets closer and closer to this obstruction, why is the water getting deeper? Why does the water pool upstream of an obstruction? Very good. Exactly right. It pools because it's gathering enough energy to get over the obstacle. So upstream, it wasn't yet affected by that obstacle, so it was just flowing at its normal depth. The normal depth being where there's equilibrium between energy loss and the downstream slope. So in the normal depth region, the flow depth is just governed by the slope of the energy grade line being equal to the channel slope. But then we get into this section where it's under the influence of the obstruction. So what we are able to measure is the depth immediately upstream of this broad-crested weir. And so here, this Y7, as I'm calling it, the depth is 3.8 meters. Okay, so the process that we're going to go through is we're first going to get some preliminaries out of the way. You know, we're going to classify the water surface profile by establishing what's the critical depth, what's the normal depth, and then the relationship between the critical depth, the normal depth, and this measured depth will tell us whether it's a mild or steep slope, and then it'll also tell us whether it's in type 1, type 2, or type 3. Does anybody remember how we know whether it's a mild or a steep slope? Like, what's the rule, like the if, the then, for the depths that tell us whether the slope is mild or steep? Good. All right. So these first two parameters we have to calculate, critical and normal. If the normal depth is greater than the critical depth, then that means it's mild. So that means that normally you'd have subcritical flow if the normal depth is greater than the critical depth. But if you have a shallow normal depth, if the normal depth is less than the critical depth, that tells you you have a steep slope and conditions are going to be supercritical. All right, so we'll do this preliminary stuff on the whiteboard here. We'll take a look at whether the conditions are critical or subcritical. And just for the people who are following along, at home, I will pull up the same thing on the screen. We could really use another whiteboard in this classroom. You wouldn't believe how big the whiteboards were when we used the engineering lab building next door. Oh, they were vast. The good old days. All right. There we go. All right, so we know that Q, the flow rate, is 15 cubic meters per second. And we know that Manning's roughness is 0.020. The channel slope is 0.0015. The width of the channel is 7 meters. And we've got some location where we've measured the depth is 3.8 meters. I'm going to call that Y7 just because in the figure that we've got, I suggested that we're going to divide this curve up into 7 pieces. We'll talk more about why that is in just a minute. But that's, you know, at the upstream end of the choke. Okay, so let's find the critical depth, Y sub c. It's flow per unit width, lowercase q squared divided by g to the 1/3 power. So if we have 15 cubic meters per second divided by a 7 meter wide channel, square that, divided by 9.81 meters per second squared to the 1/3 power. So our critical depth should be 0.7764 meters. And the normal depth, which we need to know in order to diagnose the flow regime, we're solving q equals a to the 5/3 power, slope to the 1/2, divided by n times p to the 2/3 power. All right, so this is a flow rate of 15 cubic meters per second. Our cross-sectional area is 7 times whatever the depth is, y sub n, 7 being the width of the channel. So that's to the 5/3 power. This is rectangular. We've got it easy for now. 0.0015 to the 1/2 power is our slope term. The roughness, n value, 0.020. And then the wetted perimeter for a rectangular channel, of course, is the bottom width, and then it is 2 times the side height. And so if we've got some normal depth, that means we've got the section on the left, the section on the right. So wetted perimeter is 2 times y sub n plus 7, and that term is to the 2/3 power. And if we put that into our solver, then we get the normal depth is 1.195 meters. Okay, so what kind of a profile do we have? Mild or steep? Mild or steep? It's a mild. So y sub n is greater than y sub c, so it's an m. Now what about 1, 2, or 3? Now as a reminder, the way that works is we can draw like a little sketch that has, here's the bottom of our channel, and then we have a one dashed line here, it's the y sub c, and then we have another dashed line here, that's the y sub n, and then that, we have 3 zones now. There's zone 1, zone 2, and zone 3. And so in our case, where is this measured depth? The measured depth of 3.8 meters is above the normal depth, so that gives us an M1 profile. M1 profile. And an M1 profile gets shallower upstream. So those are the preliminaries that we kind of need to take a look at. Any questions so far on how we began with classifying the water surface profile? All right. A rule of thumb is that when you're applying this method, you shouldn't do it in steps greater than 1/2 meter in elevation difference. So what we're doing is we're working from this location immediately upstream of the choke, where the depth is 3.8, and we're going to be going down to approach the normal depth, which is 1.195 meters. So the elevation difference is 3.8 minus 1.1 is how much the water is changing in depth. So 3.8 meters in depth is the starting. It's finishing at 1.195 meters. So that's the delta in depth. And our limit is 0.5 meters per step. If you have bigger differences than that, then you're trying to connect the dots with a sloped line when really it's curved. I mean, that's the more pieces we divide this up into, the better our accuracy will be. But then it also increases the computational complexity and the amount of time it takes us to solve it. So what that suggests is if we just use 1/2 meter steps, then we should have 5.21 steps. We want to round that up. So we're going to use 6 steps. And so what that means is we've got these depths that we're going to have. And so y7 is where the depth is 3.8 meters, right? So what we want to know is y6, y5, y4, y3, y2, y1. Okay, y1 is where it matches back up at 1.195 meters. So that's where it's back to uniform flow and the normal depth. And then up here, it was regulated by immediately upstream of the choke. So back to the sketch to remind us what that looks like. We've got that section where we know it because that's a measured depth of 3.8 meters. And then it's getting shallower and shallower because that's what an M1 profile does, is it gets shallower as you go upstream until it stops getting shallower because it's matched up with the normal depth. And so once it gets to the normal depth, it's not going to keep continuing getting shallower. It's got no reason to get shallower anymore because it's back into equilibrium where the energy loss is equal to the rate of energy loss implied by the slope of the channel. So the length of the backwater curve, what that asks is how far apart is y7 and y1. And then, so let's see what we've done already. We calculated the critical depth. That was the, I erased it, 0.77. We calculated the normal depth. That was 1.195. Those two told us what is the water surface profile, and knowing that is useful because it gives us a hint about whether it's going to be getting shallower or deeper upstream. And since it was an M1, it's getting shallower upstream. How many segments should be used is based on that rule of thumb that don't use more than half a meter depth change over this distance. All right, so the upstream and downstream depths for each segment. So what we're going to do is we're going to try and estimate what is the depth at each of these locations. Well, actually, how far apart they are. So this is the starting and this is the ending. So if we're using 6 steps, each step should be how much in elevation. So the delta Z is going to be the starting of 3.8 minus that. So that much distance in elevation, and we're going to do it over the course of 6 steps, so divided by 6. So each step should be 0.434167. So y6 is going to be this depth minus the delta. y5 is going to be that minus the delta, and I'm going to anchor that so then I can just continue the pattern. Okay, and then my pattern is correct. If I drag it down and it's 1.195, then that tells me I'm on the right track. Oh, okay, yeah, that won't work. So let me just have it do minus, let's check here. This minus that is what? 1.195. Good. So it all kind of goes together. We haven't really done anything complicated yet. We're just figuring out what will be the depths at these locations where we want to find out how far the delta Z is between each of them. Does everybody understand what we've calculated so far? We're just setting this problem up so far. We haven't really even applied the direct step method yet. This is just trying to do the preliminary stuff where we're saying, all right, we know that there is a certain spot where the water depth is 3.8. How far upstream is it to the point where the water depth is 3.366? I mean, there definitely is some location where that's the depth, right? I mean, we could have also said 3.37. because there also is some location where that is the depth. I mean, there is every depth that's between 3.8 and 1.195. We're just trying to like evenly spread out the points. So, I mean, we could have done that same method by just saying 3.8, 3.3, 2.9, 2.5, 2.0, 1.6, and 1.195. I mean, it would be about the same answer in the end. We're just being a little bit more precise in picking the depths at the locations we're interested in. All right, so create a new sheet. These were just kind of like the preliminary calculations. And I'm going to paste, so we've got access to these two formulas. I'm going to paste it so that we can see it as we're working. Let's put in the B, so that's the channel width is 7 meters. In the problem statement it says the flow rate Q, make that a little bit larger. All right, Q is 15 cubic meters per second. The slope of the channel, so that's how steep the actual river itself is, 0.0015 meters of elevation per meter of horizontal. And then the Manning's roughness of the material is 0.02. All right, so set up the following column headers. We're going to have some depth, and we're going to have the cross-sectional area that's associated with that depth. Then we're going to calculate, if it is that depth, what velocity do you have at that location? And for that location where there's some depth, some velocity, then how much energy is there at that location? We're going to have a delta E term, hydraulic radius term, slope of the energy grade line. I need to move things over a little. We'll have the average slope of the energy grade line, and then finally the S naught minus the average of the S sub F, and then the length for that segment, so then the DL in terms of meters. Okay, so we've got the column set up, but let's just remind ourselves what we're doing here. We're taking a look at how much energy is there on the upstream location, the downstream location, and then we're using this formula to calculate how far apart are the two sections based on the energy difference between the two, and then the difference of the channel slope and the slope of the energy grade line. So this is the main energy that, or like the tool that we're going to use to calculate the segment distances. All right, so our known depths were, again, 3.8. Let me just actually copy and paste this over. So I'm going to copy, Control-C, and then I'm going to paste the numbers rather than pasting the equations or something. So paste values, that liberates me from whether the references are right. And I have to spread them out a little bit. So I need to have a gap space in between, as you'll see why. I want to have a gap row between each of the depths. Well, that's a small little narrow place to grab. There we go. This is not a high precision mouse. All right, so these are the depths. Now, how do we calculate the area for this depth? Well, the channel is 7 meters wide, and it's a rectangular channel. So area is just the width of the channel, I'll anchor that reference, times the depth. So if we've got a depth of 3.8, then the cross-sectional area at that location is 26.6. And then I can apply that formula all the way down for the other depths as well. Let me get rid of all these locations where the answer is 0. And then just to clear the clutter, reduce the number of significant digits that are displayed. All right, what about V? Well, if we know the flow rate, Q, and we know A, then we can calculate V at each of these locations. So V is Q divided by A. Okay, so we've got a velocity at each location. I just am reducing the amount of precision. So we drag that down through all of them. I'll delete all of the nonsensical divided by 0 warnings. Okay. Any questions so far on what we're doing? So how much energy is there at the location where the depth is 3.8? Well, the energy is in two places. It's in the depth, y, and the velocity head. So plus v squared divided by 2 divided by g, 9.81. So that's how much energy there is when the depth is 3.8. The water's moving pretty slow, so there's not much velocity head. I can distribute that all the way down and get rid of these intermediate spots. I guess I could do that at the end, but I don't want to. Okay, now this is why we put in the gap, is we want to know how much energy was lost between these two sections. So remember, 3.8, that was here at section 7. So between section 7 and section 6, how much energy loss was there? So the delta E is this energy, we're actually doing the upstream minus the downstream. So it's going to be negative. So the delta E should be negative. So I'm going to copy, Control-C, and paste at each of these wrong spot. Paste. Pasting just pastes the formula. So that's how much energy is different from the upstream versus the downstream. Any questions so far? Sure. It's the depth and the velocity head. So v squared divided by 2g. All right, if it's rectangular, then what will be the hydraulic radius for a rectangular channel? Remember, hydraulic radius, the definition of hydraulic radius, we don't see it a lot since we usually solve Manning's equation where it's a to the 5/3 and p to the 2/3. But hydraulic radius is area divided by wetted perimeter. So if it's rectangular, then of course the area is just b times y. So area is b times y. Wetted perimeter is b plus 2y. So let's calculate the hydraulic radius for each of these. The hydraulic radius is going to be the area divided by the wetted perimeter. So bottom width plus 2 times the depth at that location. Area divided by wetted perimeter. Wetted perimeter is just how much of the perimeter is it in contact with the water. Okay. Drag that all the way down through. S sub f. What we're doing here is we're using Manning's equation to tell us what would be the slope of the energy grade line at a certain location that had these geometric characteristics. So if you had this certain flow rate, and if you had an n value, and a known area, and a known hydraulic radius, what slope of the energy grade line does that imply? Okay, so we've rearranged Manning's equation. This is just Manning's equation. Rearranged it to solve for S sub f. So let's see if we can put this one in. So it's the n value, anchor that reference, times the q, anchor that reference, divided by the cross-sectional area, divided by the hydraulic radius to the power of 2/3, so 0.66667, and then all of that is squared. So it's telling us what would be the slope of the energy grade line at the location where we have a certain specific depth. Okay, so I think it's such a good habit to not show all those digits. In the end, it just makes the spreadsheet so much easier to look at and debug if there are problems. All right, so I can drag that down through if all of my cell references are set up correctly. It looks like they are. All right, now this average is asking what's the average slope of the energy grade line between the sections. So at the midpoint, what's the slope of the energy grade line? So remember, what is the energy grade line? If we go back to this original sketch here, it's the dashed line that's above the water surface by the distance of the velocity head. So we've got an upstream and a downstream location, and we want to know what's the slope in the middle, because that's what we're going to use to calculate the new depth. And so the average is just going to be this one and that one divided by 2. So that's the slope of the energy grade line at the middle between two locations. And I apologize that we are now into late territory, but I'm going to continue the example. I'm going to steal your precious time. Hopefully just maybe 2 minutes will be enough, and then I'll pay you back with interest. All right, so we've got the average slope of the energy grade line, and then we want to find the difference between the water surface slope, which is known, and the slope of the average of the energy grade line. So equals the water surface slope minus this average that we've calculated. And then finally, we can calculate the segment length. Okay, so the segment length is the delta E, this delta E, divided by this S naught minus the average slope, so that. And let me format that so it's not scientific. I'll just go general there. So it tells me it's 300 meters upstream to go from the location where the depth is 3.8 to 3.336. It takes you 300 meters to get to the location where it's got that new depth. So each of these segments, what we're calculating is the distance upstream, and then we add up the total. It's the sum of all the segments. And so how far do we have to go upstream for it to be back to normal, uniform flow? We have to go 2,429.78 meters. So here in the example where it asks what is the length of the backwater curve, the length of the backwater curve is the sum of all the individual segment lengths. All right, so 12:17. I apologize for keeping you late, but it's because I gave you a little extra time on the quiz. So hopefully it was worth it. We'll meet again on Tuesday of next week and use a different method that's a little bit more sophisticated than this, because this can only be used if the channel geometry doesn't change. And we need to do better than that for non-prismatic channels like the Ohio River, where the width of the river is constantly changing. So we'll look at a different approach when we get together in class on Tuesday. Sorry we had to rush through this, but the example's in the recording if you need to refer back to it, or feel free to stop by during my office hours. So see you Tuesday.